Hello, my name is Stanford Gibson. I am the Sediment Transport Specialist at the Hydrologic Engineering Center. And today we're going to talk about a new feature in HEC-RAS version 6.1 called the Riprap and Scour Calculator. The Riprap and Scour Calculator was funded by the Regional Sediment Management Program, and it's kind of the headline feature of version 6.1. And so in order to get to the Riprap and Scour Calculator, you're going to have to go to the hydraulic designs function. If you have never been in the HD tools, you might be in for a surprise. There are a number of very cool calculators that are essentially RAS post-processors. RAS computes hydraulic parameters, and then we use the HD calculators or the hydraulic design features in order to kind of post-process those into some sort of hydraulic design or sediment transport tools. And so to get to the hydraulic design features, you're going to go either to this HD button right here, or you're going to go to Run Hydraulic Design Functions. And that's going to open up this editor. Now, there are a number of different hydraulic design computations you can do in RAS. If you go to type, you can see all of them. Bridge scour is the Federal Highway Administration HEC 18 analysis, and it is one of the most popular analyses you can do in RAS in general, let alone the HD editor. But then there are a number of other cool tools here. We've got a sediment transport capacity calculator, which is a way you can look at sediment transport capacity without doing a full-blown sediment transport model. Some stable channel design tools, which are really useful if you're, say, trying to design a restoration channel or something like that. But the new tool is right here. It's number 2. It's the Riprap Calculator. And so we're going to click on that. And like RAS Mapper, we wrote this in .NET. And so RAS is going out of process. So it just takes a second to load. But this is the Riprap and Scour Calculator. Now, the first thing you'll notice is that it has a very different look and feel of the rest of RAS, and that's intentional. We actually used the Riprap Calculator to experiment a little bit with the RAS 7.0 look and feel that we're developing the rest of the software in. And you notice that it's just a more modern software, cleaner look, and we've got these kind of feature ribbons that you'd be used to from, say, any sort of Microsoft Suite project. But this is the Riprap Calculator, and the idea behind the Riprap Calculator is that the Corps of Engineers has a very specific process that we use to size riprap. It's called Engineering Manual 1601. And really, it's all built around what we call the Maynord equation, which is the equation we use to compute a appropriate riprap size for a particular bend in the river or some sort of tow protection. And so what we've done is we've taken that analysis and we've put it in RAS because it uses RAS results anyways, and that kind of standardizes the process for our agency and the other folks who use our software. In future versions, we'll have other riprap approaches including the Maricopa County approach. But for now, this is the riprap design approach from EM 1601. Okay, so what you'll see is that we immediately bring in some hydraulic parameters. But the question is, where should these hydraulic parameters come from? Which cross-section should you define? Well, what you'll see is if you go into the cross-section is that we have a river bend here. And now this is a completely fake model. This is an idealized model that was developed just to simplify this analysis for educational purposes. It comes with RAS, but it shouldn't be used for engineering or research purposes. But in general, if you're looking for, where is the location of maximum scour? Where are things most likely to scour? Where would you need the biggest rock? It tends to be on the downstream end of the outside of the bend. If you think about how rivers meander, they tend to move that way, right? And that's because that's the region of maximum shear. And so the outside and downstream end of a river bend is where you're going to have the maximum shear. So this is going to be our design cross-section right here, 3100. But the Maynard equations were not developed for the velocity at the cross-section itself. The velocity at river bend cross-sections is fundamentally multidimensional. There's lots of helical flow stuff going on. It's just not a one-dimensional problem. And these equations were developed for not only one-dimensional flows, but idealized one-dimensional flows. When Steve Maynard developed these equations, he had a riprap testing facility, and he keyed the stable rock, not off the velocity in the bend, but off the velocity upstream of the bend. And so the Riprap calculator and some of the bend scour equations that we're going to handle in the next video don't actually use the velocity for the design cross-section, but for an upstream reference cross-section, a cross-section upstream that isn't deformed by the bend, but actually is a relatively symmetrical run or crossing cross-section. Now, this is an idealized cross-section, so all of these are trapezoidal. But if you were to look at, say, a real model, this is actually the Sacramento River, and you look at a real bend in a real model, okay, here is an actual bend in the Sacramento River. And so if we go look at what these cross sections look like, let's just kind of walk downstream. These are crossing cross sections. They're relatively symmetrical, kind of like you would expect that a one-dimensional model will do quite well here. But as we step into the bend, we end up with these highly asymmetrical cross sections where multidimensional forces are really engaged. So in this case, in the case of the Sacramento, you would want to analyze your riprap at the outside of this bend, but you would use the symmetrical crossing cross section upstream. And so we call that the upstream reference cross section. And so in the Riprap calculator, you're going to need to define two cross sections. If you go to edit, you have the upstream reference cross section, which we decided was going to be 3,500. And then you have the design cross-section, which is going to be 3,100. Now, nowhere in the Riprap calculator, as it currently stands, does the Riprap calculation, the USACE Riprap calculation, use this design cross-section. It's all keyed on this upstream reference cross-section. When you move to the scour depth analysis, then some of these will use the design cross-section, and the Maricopa County methods that we're putting in also use the design cross-section. But for now, if you change your design cross-section, it won't change your riprap at all. Okay, so what you see is that we went in and we got an average velocity, a hydraulic depth, and a width from this upstream reference cross-section. That's actually all the hydraulic parameters you need for the Maynard equation, and we pulled them directly out of RAS. In this case, we only have one flow. If you press this drop down, it'll give you all of the profiles from your steady flow analysis. And the question is, which flow should you use? There's a section in the RAS manual about how to choose your flow. It's supposed to be the flow that gives you the maximum velocity in the banks, but sometimes it's going to be a channel forming discharge or just some sort of recurrence interval that you've decided based on some sort of external risk and uncertainty analysis. But in this case, we only have one flow, so we're going to choose it with that drop down, and then we're going to put in our data. Now, all the data here under intermediate computations, if the box is gray, you don't have to put it in. Some of these already come with defaults, and so really there are only two things you have to put in here. One is the radius of curvature, and there is a section in the RAS manual about how to compute the radius of curvature, but generally you're going to fit a circle to the bend. The actual radius of that circle is your radius of curvature. Now you have to be careful about bends that bend on multiple scales, what we call fractal or compound bends. There's a section in the RAS manual that talks about that, but let's say here that the radius curvature is 300 feet, and the side slope angle is 25 degrees. In a lot of places in RAS, you put side slope in at like vertical versus horizontal. Here, we're actually just going to put it in degrees. And in the RAS manual, there's a conversion equation. And then the safety factor, well, I'm going to use a safety factor of 1 because I actually want to see what the actual size of rock is without inflating it with a safety factor before I decide explicitly and externally what my safety factor is going to be. But it's worth noting that EM 1601 does recommend a safety factor on Maynard's equation of 1.14. Right, and then the unit weight of the material, this is the dry unit weight of the rock, generally is between 150 and 165. The Riprap calculator has the ability to switch back and forth between size and weight, and it will use this to do the conversion. And then the angle of repose, which is only used in one equation in one non-default algorithm. So we put a default in there for you. You can change it if you want, but it may or may not change your results based on what you've done. Then finally, Maynard's equation has several coefficients out in front of it. These coefficients tend to be categorical. They're categorical coefficients that have a certain value based on certain choices that the modeler is going to make. And so what we've done is we've actually, instead of having you put those coefficients in, we've given you the categorical choices up in this ribbon up here. And so you can choose, is it natural trapezoidal? Is your rock angular or rounded? Where is it? Is it on the outside of the bend, which is the analysis we're doing right now, or is it straight? If it's straight, then the bend is not going to be as important, or these transitions downstream of concrete channel or at the end of the dike, things are going to be more dramatic. You're going to need larger rock, and so there are compensating issues there. And so the one that's pretty interesting is the rounded angular number because the rounded coefficient is about 25% higher than the angular coefficient. And this is just really important, just kind of as a heuristic to keep in mind, is that a lot of times you'll be in a project and there'll be project sponsors or stakeholders that are really interested in rounded rock for the aesthetic value. They don't really like the look of riprap, they'd rather go rounded, and that's fine, but it's important to recognize that right off the bat, rounded rock has to be 25% larger by diameter, but because that size is cubed, the 25% larger can be 100% heavier. And so, you just have to make that decision explicitly, and this tool gives you the option to do that. And so you can see here that we have already calculated the D30. That's what the Maynard equation does. It calculates the D30 of stable riprap given the hydraulic parameters at the upstream reference cross-section. And so actually that's pretty straightforward, right? That's a pretty painless process compared to the way it used to be. We already have a D30. We have a D30 in the bed and a D30 in the side slope. We report this in inches. And you'll notice that the side slope D30 is bigger because it has the gravitational component. And so it needs to resist the gravitational component and needs to be bigger. All right, but we're not actually done with the computation yet because all we have is D30. And if you go to a quarry and you need to specify a rock, you can't just specify the D30, you have to actually specify the full range, and you have to decide how thick should my riprap lift be. And so you're going to need actually a gradation. And so to associate a gradation with these D30s, we've built an interactive tool over here. This interactive gradation selection tool starts out by populating these default gradations from EM1601. EM1601 has some kind of like idealized default gradations. You notice these aren't lines but areas because they give you a min and a max for like a D10 and a D50 and a D100. And so we've actually populated every other one of these 1601 gradations, but you can see that our D30s are plotting here. The brown D30 is the bed, and then the green is the side slope. And what you're going to do is you're just going to select one of these gradation curves to associate with those D30s. But what I want to do is I want to get a little more resolution here. So I'm going to go to gradations. I'm going to go to these EM1601 gradations, and I'm going to turn off the big ones because the big ones are too big and they're just not going to matter. And I want to add more resolution at the low end. And so now we have these 1601 gradations 1 through 5, and they're all there available for us. And so what we can do now is we can either click bed up here, or we can click this radio button and go select whichever one of these gradations should be associated with that D30. And it's going to be this one, right? This is the one, the next one larger. And so I'll click on that. And what you see is it goes in and picks off the D100 from up here. It also picks off the D50, but you can't see that. And then it computes a thickness. And EM1601 uses the equation, your riprap thickness should either be 1.5 times the D50 or 1 D100 thick. And the idea there is that you don't want your riprap to be prone. So your riprap thickness should at least be the size of your biggest class, so your biggest class doesn't stand out. But it's going to be the maximum of either 1.5 times the D50 or the D100. And so we'll compute that for you and then report the thickness. Okay, now I want to associate a gradation with my side slope D30. And so I'm either going to come up here and choose side slope, or come down here and choose this radio button. And now this is active. And so I'm going to come over here and choose this one because this gradation would be the most appropriate for that computed D30. And it goes off and picks the D100 and then looks at the max of the D100 then D50, which is 18 inches. And we're done. We actually have computed the D30, the D100, an associated gradation, and a thickness for both our bed and our side slope. Now, a couple of things that are interesting here. One is, how do you know you chose the right upstream reference cross-section? Well, you don't, and it's actually sensitive to that result. And so one of the things you can do is you can flip through these and look at the sensitivity. And so you can flip from 3500 to 3600 and look at how that changes the results. And, or if maybe that all changes too quickly for you, we have this tool that's similar to the persistent cross-section tool in the cross-section editor, which is one of my favorite tools in the cross-section editor because you can look at how things are changing upstream and downstream. And so you can say, hey, keep the previous D30s on the plot. And now I'm going to switch my upstream reference cross-section, and you'll see, oh wow, it's actually very sensitive to which of these cross-sections I choose. And so that can help you look at, what is actually the maximum case? What is your range of uncertainty based on which upstream reference cross-section you key to? The gray are calculated from previous, and the brown and green dots are the calculations for the cross-section you're in right now. So we added that capability to look at the sensitivity of your result to the upstream reference cross-section. All right. The chances that you actually have access to these like idealized platonic 1601 gradations out there in the world is very unlikely. It's very low. And so we've given you the ability and actually recommend that you define your own gradations. And so that's what this button does. If you press this gradation button, this actually helps you manage a bunch of different gradations as well. But we can turn off the default gradations and add our own. And so we're going to add a gradation here. And I'll just call this Bob's Quarry. This is and grad 1. This is gradation 1 from Bob's Quarry down the street. And you have to define a D30 and a D100, and you should define a D50. These are the things we need for the calculation. So those are compulsory. But let's say that Bob, he also likes to define a D1 and a D85. And so we're going to put in those percentiles. And then you can define it by weight, which, those of us who come to this from a sediment transport perspective, we're used to our rocks having size, right? But people who are coming from the design point of view often define riprap in terms of weight. I'm going to switch this to size, but you can define it in either, and it computes back and forth based on this unit weight. And so let's give this a very simple gradation: 4, 5, 6, 7, 9. Okay, and then let's actually define a couple more. Bob has a couple of different types of material in his quarry, and so we're going to add an 85 here, and we'll go 5, 6, 7, 8, 9. And then let's do just one more. This is Bob's super coarse gradation. And we'll call that 8, 9, 10, 11, 13. Okay, and so now I have these 3 customized gradations, and I'll turn those on and apply all. And now when I close out, we get these 3 curves. And now I put in curves instead of regions. You can go in and put in a region if you want, but we've got these curves associated with the actual gradations that are available to us at a local quarry. And so now what I'm going to do is I'm just going to go here and I'm going to say, hey, this is the D30 I'm computing there. This is the rock I have available to me that's most appropriate. I'm going to click on that. And now it's going to recompute the D100 and the thickness based on the rock that's actually available to me. And then I'll go down to the side slope and I'll click on this one because that's the most appropriate one for that, and it recomputes the D100 and the thickness. Now, of course, I could go in and define a region. So let's go and define one more, except instead of curve, I'm going to do max min zone, where you can go in and put a min and a max weight and a min and a max size, and that'll give you a result that's similar to one of these defaults where you get a region, not just a single line. All right, then finally, we have another cool tool up here that just kind of switches between weight and size. I've done everything in size because I'm a sediment transport engineer and I think about rocks in terms of size, but now I'm going to go across the hall and talk to my design engineer who thinks about things in terms of weight. So I'm just going to convert everything over to weight. I'm going to switch over to the EM1601 gradations again so you can see how it works with that. So I'm just going to push this button and you'll see that everything gets switched to weight. The stone weight is now in pounds. It's percent finer by weight. And the D30s are now defined in terms of weight, and the D100s also in terms of weight. The thicknesses are still converted back to inches, and you'll notice we haven't actually changed any of the results, and so we still have the same thicknesses because it doesn't really make sense to define a thickness and weight. All right, so that is the first tool. Now we've defined our riprap size, but you can't go in and protect a bank without protecting the toe. One of the biggest failure modes of bank protection is toe scour, and so you always need to put in some sort of toe protection, whether it's keying or a launchable toe. And to figure out how much of that you need to compute the scour depth. And so that's what the second tab is about, and that's what the second video is going to be about: how to go in and compute the scour depth required for your launchable toe. But for now, that's a introduction to the Riprap Calculator, the new feature in HEC-RAS 6.1. This tool was coded by Zach Morris, one of the developers on the RAS team. I was supported very heavily by the Corps of Engineers SMEs on Riprap and Scour design. That's David May and David Biedenhardt and Chris Herring. And this whole effort was funded by the Regional Sediment Management Program of the Corps of Engineer, known as RSM.